you very much. Yeah, you all see if I write on this blackboard here? Okay, okay. So, our setting is the classical one. We are in R2N with the standard symplectic form, dpj, dqj. So I use the physical notation p and q. And so my talk today is about an old and somehow fundamental question. So how rigid are symplectic diffeomorphism in comparison to volume-preserving ones? What are the things which a volume-preserving diffeomorphism can do, and instead a symplectic one cannot? And of course, elementary things. For instance, if one has a fixed point which happens to be a hyperbolic, then of course in the symplectic world, the stable and unstable manifolds have to have the same dimension. For volume preserving, they have just to be both positive dimensional, and that's it. But instead, to find more, say, refined things, the most well-known result is the non-squeezing theorem of Gromov. Let me recall the statement. Non-squeezing. Gromov. So, no symplectic diffeo maps the ball of radius r into a cylinder, say P1 Qn with P1 squared plus Q1 squared less than S squared if R is bigger than S. Okay. And so this is a sort of two-dimensional rigidity phenomenon. The base of this cylinder has dimension 2. And it has been a long question whether there are also sort of middle-dimensional rigidity phenomena, because after all, a symplectic diffeo preserves omega, so it preserves all its powers. So it seemed to be reasonable that there should be also middle-dimensional phenomena. And the prototype of this was, so people looked at the question of what happens about considering the embeddings of polydisks. So if I have a polydisk, so B1, BRN, so these are two-dimensional balls. This is in the plane, I don't know, P1, Q1, P2, Q2, etc. And I ask whether this embeds into BR1 prime cross BRN prime. Then, by means of a symplectic embedding, then there are so there's an obvious obstruction which is given by volume. So R1 prime, R2 prime, product Rn prime has to be greater or equal than R1 Rn. And then instead, Gromov's no-squeezing theorem tells us that the minimal radius Ra prime has to be bigger than the minimum of Ri. And of course, the question was whether also other products of these radii play a role. And some years ago, in 2008, Guth actually ruled this out. So there's a construction by Larry Guth which shows that so there is a constant depending on the dimension n, such that if I have, so if, let's put it here. R1 prime, Rn prime is bigger than this constant R1 Rn, and also the minimum of Ri prime is bigger than this constant, the minimum of the Ri's. So if we have these inequalities, say, but just up to a constant, then there exists a symplectic diffeo phi, which does this thing here. Okay, and so when I first heard about this result, so this was like 4 years ago in Oberwolfach, Helmut Hofer gave a talk, an evening talk about this construction, and the title was somehow the title was Life After Guth. So in some sense the thing was that such a result could imply that there are actually no more, say, no middle dimensional phenomena to be found out in symplectic topology. And so in some sense, at least if we think about these basic questions, we already know what one should know. And yeah, I was also very impressed about this, because I also, so like probably anybody else, believed that this was not possible, and so I started thinking about sort of a different way of thinking about such a phenomenon. And so the aim was to try to understand why one can do these things in symplectic topology, but in order to do this, polydisks are a bit too complicated, and so I would like to stick with the ball as domain of my symplectic diffeo, and to start by, so we start by rephrasing the Gromov no squeezing in an equivalent way like this. If we have phi from the ball into R to n symplectic diffeo, then we can say that and so let's call P, this is the projector onto the P1, Q2, P1, Q1 plane. Okay, orthogonal projector. And then one can reformulate Gromov theorem by saying that the area of the projection of the image of the ball of radius r is greater or equal than pi r squared. Okay, this is so apparently this is a stronger statement, because of course the area of the projection could be small without being contained in a disk, but it's actually equivalent, because you can always, you look at this projected set, and if this does not hold, if you have the other strict inequality, then you can always, by means of a area preserving map into a disk of small radius, and you get you violate Gromov statement. So this is Gromov. Okay, but if you write it in this way, there is an obvious generalization, say tentative generalization. Instead of projecting onto this P1, Q1 plane, one projects projection onto P1, Q1, PK, QK space. Again, orthogonal projection. And one asks whether it's true that the 2k dimensional volume of P phi BR, so let's put a question mark, is bigger than the corresponding, the 2k dimensional volume of the corresponding ball of radius 2k. Okay? This is the question. So in some sense, the question is whether, yeah, the 2k, so Gromov's statement says that the two-dimensional shadow of the image of this ball has big area, and now we ask whether the 2k dimensional shadow of the image of the ball has big volume. And a couple of observations. So, well, so this is true for k equal 1 by Gromov, and it's trivially true for k equal n because it's volume preserving, so we have inequality. So in some sense, it's an interpolation between Gromov and Liouville. And another observation is that if you want to formulate this way with a volume, you need to use also the Euclidean structure of R2n. But of course, if you want to avoid it, you could take, if you want to use only the symplectic structure, you can take any symplectic vector space, subspace. You project, you consider the symplectic projection, which means that you project along the symplectic orthogonal, and then you replace this volume by the integral of omega to the k divided by k factorial. Okay, so I will use also the Euclidean structure because we have it, but it's a symplectic statement. Okay, so I want to discuss a bit this statement, and a first result. Oh, I should also cite my co-author. These results are joint work with Slava Matveyev from Leipzig. Okay, so the first result, let's call it linear non-squeezing. Says that this is indeed true when the symplectic diffeomorphism is linear. So if phi is a linear symplectic isomorphism, say automorphism of R2n, then the inequality holds, volume 2k of pi phi. Well, here, of course, we can consider just a unit ball. When I just write B, I mean the unit ball. And this is greater or equal than omega 2k. And I just need another thing. The equality actually holds if and only if I take the image of R2k. R2k is the space spanned by the first, so P1, P2, Q2k by the first coordinates. If I take the image by the adjoint of T, if this is a complex subspace with respect to the standard complex structure that we have, then we have equality. And here, of course, this is linear algebra. It's easy, but let me just say what are the ingredients, because we will use them later. So the ingredient is basically that when one has a map, say from Rn to Rh, a linear map, linear and onto, then if I want to compute the volume, the h-dimensional volume of A of the ball, say divided by omega h, then this is, one has formulas like, this is, for instance, the determinant of A transposed 1/2. or also, so this is an automorphism here in RH, or also the maximum overall sub V in the Grassmannian of also subspaces of dimension h in Rn, so V in the Grassmannian of dimension h in Rn of the determinant of A restricted to V, which makes sense because now V and RH have the same dimension, so they are, here we always have this Euclidean structure, so the absolute value of the determinant is well defined. Okay, so this is the ingredient one uses, and then the other thing one uses is what is called Behringer inequality, the fact that omega to the k, the mass of omega to the k is realized on complex planes and something like that. Okay, so this is the linear thing. Then a second result is, say, let's call it, let's permute the words, nonlinear squeezing. So in the smooth, in the symplectic, for nonlinear symplectic map, this is false. So if one strictly less than k and strictly less than n, and then epsilon, for every positive epsilon, there exists phi symplectic, such that the 2k dimensional volume of P of phi of the unit ball is less than epsilon. Okay, so when we are in intermediate dimension, then this image of a ball can have this shadow with arbitrary small volume. And the construction of this counterexample, so this is an example, and the construction uses exactly some of the construction that Guth introduced in this paper. One has just to arrange them in a different way. And of course, so this map is extremely nonlinear, because, for instance, so the image is something which has all its two-dimensional shadows, even on symplectic planes, have big area. Nevertheless, this I don't know, four-dimensional shadow has small volume. So the map is really nonlinear. And so a natural question is, where is the, so if you have a statement which is true in the linear category and it's not true in the nonlinear category, what is the borderline? Is it because this map is really nonlinear, or it's already enough to have, I don't know, a small perturbation of a linear map to exhibit this phenomenon? And formulating this question in terms of when the initial domain is the ball, I think it has the advantage that one can make this, say, local question very precise. And so one way of putting this local question precisely is, for instance, I fix phi a symplectic diffeo, and I fix also a point, for instance, the origin, and I ask, is it true? I fix also P, the projector. P is always an orthogonal projector onto a 2k dimensional plane. And I ask whether the 2k dimensional volume of P of phi of a ball of radius r is bigger than omega 2k r 2k for every r small. Okay, this is one way of formulating the local question. Another way is I can consider a path phi t in 0, 1 of symplectic diffeos, say a smooth path. Say that at 0, phi 0, let's call it big phi, is linear. And then the question is whether the volume, again, the 2k dimensional volume of p phi t. Say this time I can work with a unit ball, fix the ball, and the question is whether this is greater or equal than omega to the 2k r, sorry, just this, because it's the unit ball for small t. So I perturb a bit a linear mapping, and I would like to see if, at least at the beginning, I have the inequality. Okay, so, and of course, a positive answer to this question would imply a positive answer to this other one just by rescaling near the point. Okay, and here, so I'm absolutely convinced that both these results are true, and we have two results now which give, I think, pretty strong evidence that these are true, although they are not still a proof of these. So let me start with the first one. Let's call it a proposition, and let's call it just a generic local non-squeezing. This is in the first formulation, the one when I fix the map. And so I fix the map, and I can say that there exists a set. So I fix my symplectic diffeo says is from R to n to itself. Then there exists a set U in R to n, which is open and dense, such that for every x in U, so if I put the center of my ball in U, then the local squeezing, non-squeezing holds. The volume, so there exists R0 which depends on x, positive, such that the 2k dimensional volume of P of the ball of radius of phi of the ball of radius r center x is greater or equal than omega 2k r 2k for every r smaller than r0. Okay, so at almost, so on an open dense set, this is true. And yeah, I don't want to call this a theorem because, I mean, as I said, I think that U should actually be the whole R to n. And also because actually the proof of this at some point uses an argument from geometric measure theory, something about minimal submanifolds, which is a non-trivial thing, and so it's not really satisfactory. One would like to have a decent proof, elementary proof of such statements. And maybe let's say something about this argument at the end. Before I would, yes, sure.
This statement is just like a stability statement, right?
Yes, so it's
differentiate t equals 0.
Exactly. In fact, this is exactly now we want to differentiate in t equals 0 and see what happens. Exactly. This is what we but I mean, differentiating this function is this is what I will describe, but it's took me several months to compute the derivative. So but before stating this other result, I need just some preliminaries. So what do I need? So when I have a curve, say from periodic, from period 2 pi, with values in R to n, I will denote by, so E is just its Dirichlet energy, 1/2 integral 0 to pi of z prime squared. This is the Dirichlet energy. And by A, I will denote the symplectic area bounded by z. So this is the integral of z star lambda, where lambda is a primitive ei dqi, a primitive of the symplectic form to n 2 pi z. So energy and area. The other object that we need is well, we said that R2k, the space spanned by the first coordinates. This, we have also a complex structure, can be identified with ck. And we will consider the Grassmannian of lines, the complex Grassmannian of complex line in this ck, which is nothing else than the complex projective space of dimension k minus 1. And on this Grassmannian, we will consider the, so let's call omega, it's a standard Kähler form on this Grassmannian. And by me, I will denote the volume form which is induced by the standard Kähler form. So it's, I have to take omega to the k minus 1 exterior product by itself, and I will divide it by k minus 1 factorial. So this is the volume form on this Grassmannian. Okay? So these are the objects I need in order to state the theorem. Now the theorem is, so let's call it a second order expansion. First thing, so we would like to, where should I write this? Maybe here. So we would like to, our question is whether now the 2k dimensional volume of the projection of phi t of the ball is greater or equal than omega 2k for t small, okay? And we know that phi 0 is linear. So of course, if here at 0 we already have a strict inequality, then the result will be true by continuity. So we can assume now that for the linear mapping is such that we have actually the equality, which means that we are assuming that phi t of R2k is complex. This is our assumption. And now in order to make, so we have a formula which works in general, but in order to make things easier in this presentation, I will just assume that phi is the identity. So we're just perturbing the identity, which is enough. So now we have this phi of t, so this is path of symplectic diffeos, and phi of 0 is the identity. And then, so the volume, the 2k dimensional volume of p of phi t of the ball, this is equal to omega 2k, then there is no zero order term, and there is a term, let's call it c, then let's see what it is, c plus t squared plus big O of t cubed for t going to 0. And I have to tell you what this constant c is. Another thing, so this path of symplectic diffeos is generated by a path of Hamiltonians. So we have dt of phi t. This is some Hamiltonian vector field ht of phi t. Okay. So this will be every path of symplectic differs here in R2n will be generated by such a thing, and so we have also these Hamiltonians. And so this number C, so where C is this object here. I write the expression for C. C is the integral on the Grassmannian of complex line in CK of the energy of a path, let's call it ZL, minus the area of the same path ZL. This integral is computed of this function with respect to the volume form mu in L. So L here is in this notation, L is an element of the Grassmannian. It's a line. It's a complex line. Okay? And these paths here, ZL, this is a loop. ZL of theta is, I take my Hamiltonian vector field H0. I take its component, not the component on CK, but the orthogonal component, and evaluate it along a circle, so e to the theta j, let's call it ZL, where this ZL is an element of this line intersected with the boundary, with a unit sphere in CK, the boundary of this 2k dimensional sphere. Okay, so let's see what this does. So we have, we have our, let's try to make a picture. This is our CK, and then there is this Cn minus k. And what matters in this computation is this sphere here, the unit sphere in CK. And we are interested here, so we look at the component, so the Hamiltonian vector field will do something. What we are interested in is in the component, this component here. And then we evaluate, we have these loops, which we consider only, not all planes, but only planes which are actually complex lines. And we go around them, and then we consider this loop. Okay? So after, many weeks of computations, this is what one gets, which find, so the computations are long, but at least the final formula is decent. And what is nice is that, of course, the energy of a loop is always bigger, greater or equal than its area. It's basically, so there's this area energy inequality. It's basically isoperimetric inequality in dimension 2. And so we have that the energy of a loop Z is always greater or equal than the action, with equality holds if and only if Z is really something like, it's really a circle. So it's Z naught plus e to the theta j Z1. Okay? So this formula means that, again, of course, there are cases where this constant is 0. for instance, if this phi t is just the trivial, it's always the identity. There's no hope that just by a second order expansion we can get some information. But this constant is always greater or equal than 0. And if the Hamiltonian vector field is not so symmetric that all these, this function on all these lines vanish, then there is this no squeezing. And so, an immediate corollary of this is that, so let's call this vector field Z. So if it's not true that the equality, what is it, Z of e to the theta j Z naught equals, I think it's something like 1/2, well, no, whatever. There is a condition on, you can, by using this fact here, by using the fact that we know exactly when the equality holds here, you can characterize precisely those Hamiltonian vector fields which will make this constant vanish. And these are the Hamiltonian vector fields for which I cannot conclude. So that's why I don't. But they are, of course, a very thin minority. It's a closed set with empty interior. And so again, this is a generic. You can also interpret this as a generic statement. And so this, I think, it's good evidence to the fact that the statement should be true in general. And in the last time, maybe I would like to make some. The corollary, I didn't write it, but maybe I can write the formula. So the corollary says that if this vector field here, Z, is not so symmetric that this function vanishes always, then there is no squeezing. And the formula is the formula is this: Z to the e theta j x, but it doesn't tell much. Z of x plus Z of minus x plus 1/2 e to the theta j zx minus Z of minus x. So if this is equality, say, for every x in R2k, so we have this thing here. If this statement here is false, then the volume, 2k dimensional volume of p phi t of the ball is strictly bigger than omega 2k for t positive and small. Okay, one can write explicitly the form of the vector field, just that. Okay. Sorry, the boundary of the on the boundary of the ball of dimension 2k. Yeah, it's a condition only on the boundary. Thanks. Okay, and let me conclude by making some general comments, which will also lead to the proof of the other proposition. So again, here the proof is a long computation, and I don't know, one does not learn much from it. Maybe, the thing which one could learn is how to compute the derivative not at t equals 0, but at any t, and so get the final result. But it's a bit hard.
Question.
Yes.
Can I ask whether it's obvious that the first derivative is 0?
No, not at all. But they say that computation took me, I don't know, one afternoon, and instead the whole one many weeks. No, it's not obvious. No, it's not obvious, and it's of course because it also comes from the fact that you have to use that phi is symplectic. because otherwise it would not be true. It's not obvious, no. So let me make a general. So now we have this symplectic diffeo here, and we have this map. Let's call it psi, which is projection composed phi, okay, which goes from R2n to R2k. And we know, so since the linear, we said the linear no squeezing is true. So in the linear category, no squeezing, this middle dimensional no squeezing holds. So this gives us an information. So this tells us, so the linear non-squeezing tells us that the 2k dimensional Jacobian of this map X, which is nothing else by, this is just the maximum over all spaces V of dimension 2k in R2n of the determinant of the differential of psi at X restricted to V, this object here, is always greater or equal than 1. Okay, so we know that there is some 2k dimensional plane somewhere where the composition expands volume. And so, of course, the perturbative statement would be trivial if it would be true that any map with this property also has a local non-squeezing property, but this in general is false. So this is a remark I should make. So if I have a map psi now from, say, from Rm to Rh, and m is strictly greater than h, which is strictly greater than 1, if we have this, and I know that the h Jacobian of psi is everywhere bigger than 1, this does not imply that the volume, the h-dimensional volume of the image of the ball of radius r is bigger or equal than omega h r to the h for r small. Okay? And it would actually be true when h is 1, but in general not. You can build examples. Yeah, this is a nice exercise for students to build an example, for instance, from R3 to R2 of a map with this property. And why is this not true? This is not true because there is so it's a lack of integrability in some sense. So we could do the following. So we have this condition here. We know that the Jacobian, h-dimensional Jacobian is greater or equal than 1. And so for every point we could consider, let's call it, I don't know, Wx. This is the set of spaces in the Grassmannian of dimension h in Rm, where the determinant of deep psi x restricted to V is greater or equal than 1. Okay? So by this fact here, this is non-empty for every x, and actually an element here is precisely, I take the differential of x, I take its adjoint, and I take right Rh. This space here is always in this set by this assumption. We're assuming this. H Jacobian greater or equal than 1, then at every point I have, maybe if it's 1, I have just one h-dimensional plane where volumes are expanded. If it's bigger than 1, I can also move it a bit. I have a closed set with a non-empty interior of spaces. So this object here could be called like it's like a multi-valued distribution. At every point, I don't fix just one space, but many of them. And if this multi-valued distribution, so let's call this a lemma, if this multi-valued distribution is integrable, does it mean integrable in the obvious sense? If there is a smooth foliation, which at every point is tangent to one of these vector spaces. Okay? If it is integrable, then this local statement would be true. The volume h psi of BR is greater or equal than omega h to r to the h for every r small. And the reason is just that, assume that this distribution is integrable. I take my ball, I take this foliation, which is tangent there. Then what I have to show, and this is the thing which is, at least I don't have an elementary proof, what you have to show that if you have an h-dimensional foliation of a ball, you always find one leaf whose h volume is bigger than the volume of the corresponding ball. And this you can do by, you look at the trace, you replace your leaf by the minimal object with the same boundary, and then you use monotonicity you choose among all those new minimal surfaces, you choose the one which passes through 0, and there you use the monotonicity formula. That's it. And so now one has a leaf with large volume, and on these leaves the map is volume expanding, and so also the image will have large volume. Okay? And so the question is, it could be, this also another way of proving this local no squeezing would be to show that in the symplectic case, this distribution is always integrable, and there is a bit of evidence for that, which is this. Well, some evidence is also that I tried many examples and it was always integrable, but a better evidence is this simple observation. Assume that we are in the rigid case. So assume that for every x, say in R2n, this distribution just consists of one space. So there we don't have any choice. So this is just d psi. So this is just, say, one space. Let's call it v of x. So this means that we are. This means that this space here, which is precisely d phi x transposed of R2k. This is our v of x. By what we said at the beginning about when the equality holds in the linear statement, this means that this must be a complex. At every point, this is complex. Then, in this case, v is trivially integrable. So in this case, or let's call it even v. So in this case, this is a genuine. It's not a multi-value distribution. It's a genuine distribution, and in this case, this is integrable, and this because well, this v of x is also, we said it's complex, so it's g of v of x, so it's j of d phi x t R2k, but phi is symplectic, so this is d phi x minus 1 of j R2k, but this is also complex, so this is d phi x minus 1 of R2k, And so this means that in this rigid case, these are just the counter images by phi of the foliation given by leaves which are parallel to R2K. And this is actually how you prove the first proposition, because then you can consider the generic thought. You can consider among the set of all points, you have points where you have just one space, and then you have the complement where you have more. The complement is open, and there the non-squeezing holes just by continuity. This set here, if it has a non-empty interior, in the interior you use this argument and this lemma, and also there the non-squeezing holes. So the only ambiguous points are the points which are on the boundary of this. Okay, and I will stop here. Thanks for the attention.